Ever since we were in high school, we've been able to deal with the physics of a bunch of particles that are experiencing forces. So if I have a bunch of particles, n particles, different masses, and they all experience forces, then I know exactly how to compute what happens after a while. And I compute that using Newton's second law. The forces acting on those things are just equal to the mass of each mass times its acceleration. And it's a perfectly good way of solving what happens to the entire universe. Except that the number of particles in the entire universe, and therefore the number of equations you have to solve, is extraordinarily large. And in the case of, say, a cricket ball, ridiculously large. You don't really want to be dealing with the position of each particle in a cricket ball. What you want to be dealing with are the generalized coordinates, the center of mass motion, and the angles that define the full position of all the particles in that cricket ball. So we want to take this and we want to change our expression of the dynamics into something that is much more compact and much more related to the kinds of generalized coordinates that we want to use. The way we do that is we look at the idea of work. And work is where things move through a distance while under a force. So let's consider each of these things moving a small distance. Indeed, an infinitesimally small distance, but you basically get all the right ideas by dealing with just a small distance in your mind. So you can think of these as finite or infinitesimal as you wish. So we have a large number of displacements like that. So if I have a displacement $ri, then because this thing up here is 0, then if I take the dot product of the two, then I of course still get 0. Also, if I sum all of those zeros up, I'll get 0 again. One of the more subtle problems with solving these equations from Newton is that these forces are often quite complicated. We can usually break the force on a particle down into two pieces. The first is the applied force. This is the force that you might be externally applying. Supposing all these masses are part of a cricket ball, you might grab your fingers and push on some of them, and that would be an externally applied force. But then in order to keep all these relationships the same, so that they all stay as a cricket ball rather than breaking up into a fine powder, then internal to that cricket ball there will be a large number of extra forces, and these are called constraint forces. So these are forces that make sure that this particle and this particle stay the same distance apart from each other, and that this particle and this particle stay the same distance apart from each other. And these constraint forces, therefore, can be quite powerful, and you actually have to solve for them assuming that the constraints are being held. Calculating these constraint forces for a dynamical system can be quite difficult. They appear only to enforce the necessary restrictions on the movement of the individual particles, and therefore the constraint force on each particle depends on all of their positions simultaneously, and even their velocities. The only thing we can say about them for sure is that they do not ever need a component along directions that the particles can move. This means that an ideal constraint force has exactly 0 dot product with an allowable displacement of each particle. Even though the constraint force can be potentially extremely large, it's always perpendicular to the movement of the particle. So the constraint force, even though it's there, tends to do no work. And if the constraint force does no work, then we have a very powerful result that we can take this and we can say that if we break this up into two pieces, we've got the applied part and the constraint part, then the dot product with the constraint part and these displacements is 0. So we can take this result, which is therefore a lot simpler. The reason it's a lot simpler is that we know what these applied forces are. We don't have to worry about the constraints anymore in this equation. And this equation is called D'Alembert's principle, after the famous French mathematician Jean-Baptiste principle. And that's our starting point for changing all of our mechanics from Newton's laws over into something called the principle of least action.